Hi everybody, we are ready to teach you some math. So I have two dogs that are begging for my attention. I have Zuko, and he's going to help me teach. And then also Remy's behind me. I'm not quite sure where you see him. I don't know. But here we go. Alright, so we're going to start up on page 71 of our notes. And we're going to recall the alternating series estimation theorem. And that gives us a way to say it's true that our series has infinitely many terms and it's not easy for us to find out the exact value, but we have a way to measure how far we are from the actual sum. So it might only take 10 terms or 2 terms or 5 terms before we're actually really close to the sum of all infinitely many terms. So this alternating series estimation theorem gives us a way to estimate an alternating series within a specific error range. Okay, so we'll go to example 5 now, and it says use a power series representation to approximate the definite integral I to 6 decimal places. Okay, so from our last example, we found that ln of 1 minus x. So we're going to utilize that. So from example 4, we found that ln of 1 minus x is equal to the sum from n is equal to 1 to infinity negative x sub n over n. So we don't have just 1 minus x, we actually have 1 plus x to the 6th power. So we want to fit that form so we can just use some substitution and piggyback off of the work we've already done. So let's try that. So we have ln of 1 plus x to the 6th power. We need a minus because that's the form of the ln 1 minus x. So let's write this as ln 1 minus, and then we're going to have negative x to the 6th because we pulled in that negative. So now we have the same thing except for we need to replace x with negative x to the 6th power. Okay, we can do that. So we have our sum, n is 1 to infinity, then we have negative, and instead of x, this is what we're going to replace with the negative x to the 6th power to the nth power all over n. Okay, so again, we replaced just x with negative x to the 6th power. Let's simplify that. So that becomes the sum from n is equal to 1 to infinity. We have a negative 1 to the nth power times another negative 1. So that's going to be negative 1 to the n plus 1 power. Then we'll have x to the 6n power all over n. Okay, so now that we have our integrand, so we have ln 1 plus x to the 6th, ln 1 plus x to the 6th, and we know that that equals this sum over here. So let's just retract a little bit. So we have, just write it all together. We have ln 1 plus x to the 6th equals, and then we have our sum, n is equal to 1 all the way to infinity, negative 1 n plus 1 x to the 6n power all over n. So our original problem up here wants us to integrate that. So that's exactly what we're going to do. We're going to integrate both sides with respect to x. 0 to 0.2 dx. The integral 0 to 0.2 dx. Now, I want to go back and make an important remark. So from example 4, way back up here. Whoops. So way back up here, we found that that equality was true when we had a radius of 1. So it was true for x values between -1 and 1. So that's what makes it important, that these x values that we're integrating, 0 to 0.2, they fall within this radius, -1, not this radius, this interval, -1 to 1, because those are the only x values that this equality is even true for. So we had to stick between those. Okay, so now we have our what we actually want, what the problem asked us for, on the left hand side, and we're going to do some work on the right hand side to find our answer. All right, so since we know this series converges, we can take the integral inside and we're going to integrate our general term. -1 to the n plus 1, that's a constant. We're not going to have to touch that. N is a constant in terms of our integral because we're integrating with respect to x. So the only piece that we have to really take the antiderivative of is that x piece. Okay. All right, so we're going to have our sum. Oops, that's a highlighter. We're going to have, we'll have our sum from n is equal to 1 to infinity. This -1 to the n plus 1 stays out as it is. N is down here. Now this x raised to the 6n power, to take the antiderivative of that, we add 1 and divide by that same number. So this is going to be x to the 6n plus 1, and then we divide by that same number, so 6n plus 1. So that's our integral right there. Okay. Usually for integrating we would have a plus c, but this is a definite integral. So we're actually going to put our bounds, our limits of integration, 0 and 0.2 out here. So we're going to plug in 0.2 for, these are x values. So we'll have our sum from n is 1 to infinity, -1 to the n plus 1. Instead of x, we're plugging in that 0.2, 6n plus 1, all over n, 6n plus 1, minus, and then we plug in 0 into our antiderivative. So we'll have -1 to the n plus 1. Instead of x, we're going to put 0, 6n plus 1, all over n, 6n plus 1. There we have it. Now for the second piece, it's 0 on top, so the whole fraction is going to be 0. So this whole thing goes away. That's just 0, which is nice for us because that's less work. All right, so this sum, we can write out some of these terms. So let's just write it out here. Let's start off with like n is 1, n is equal to 2, n is equal to 3, n is equal to 4, etc. Okay. So when we evaluate the sum and we first plug in 1, we're going to get -1 to the 1 plus 1, right? So we're going to get -1 to the 1 plus 1, which is squared, and then we'll get 0.2, oops, getting crazy, 0.2 to the, we're still on n is 1, 0.2 to the 6 times 1, so 6 plus 1, so to the 7th power, all over n is 1, so 1 times 7, so 7. Okay. Then for n is equal to 2, so these are kind of off. I don't want it to throw us off. So let's just rewrite those as n is equal to 2 over here. And now we're plugging in 2 for n into our sum here. Okay. So if we plug in 2 for n, we're going to get -1 to the 2 plus 1 power. So that's -1, 2 plus 1, that's 3. And then we'll have 0.2 raised to the 6 times 2, so 12 plus 1, that's the 13th power, all over n is 2 times 13, so that would be 26. Plus, now let's do n is equal to 3, so that would be -1 to the 3 plus 1, so the 4th power. Then we have 0.2, 6 times 3, that's 18, plus 1 is 19, all over 3 times 19, so 57. And then I feel like we're just going to evaluate these and see if we have enough. If not, we'll go back and add more terms. Okay, so this is where this estimation theorem comes up. So let me scroll up slowly so we don't get dizzy. So this estimation theorem says that the original sum compared to just the sum of the first n terms is the difference between those. So the error is less than the next b sub n term. Okay, so what we can do, remember b sub n is the positive part of the alternating series. So for each of these, let's scroll back down, nice and slow. Okay, so for each of these, I'm going to evaluate the b sub n part. So just everything but that -1 power. If I put that into my calculator, so I'll put 0.2 raised to the 7th power, and then divide by 7, and I get 0 point, and then I have 1, 2, 3, 4, 5 zeros. 1, 2, 3, 4, 5 zeros after the decimal place, and then 1 8. So again, I just said there was 5 zeros. Our problem, it said it wants this correct to 6 decimal places. So we want zeros for more than 6 decimal places. Okay, so we're not quite there yet. So now let's go on to the next term, so the b sub 2 term. And if we put this into our calculator, 0.2 to the 13th power divided by 26, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros. So I think we made it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then 3, 1. Okay, so this is less than the error that we want. So our alternating series estimation theorem, so let's just make a note. This is less than our error. Okay, which said 6 decimal points. So we have 0 for 6 decimal points. That tells us that we're good to go. So our b sub n, which was this number that I can't even say because it's so little, that number is less than, our error is less than that number if we just add the first term. That's what our alternating series estimation theorem says. So you go and you calculate the b sub n's until you get less than your error, which we did. Once you get less than your error, it tells us that we only need all the terms in front of it, which for us, it was only one term. So that's crazy. We only need the first term of our integral of our series to be extremely close to the actual series as if we added all infinitely many terms. That blows my mind. So, since we're estimating this within 6 decimal places and we only need the first term, we can conclude our answer. So we would say our integral, which is 0 to 0.2 of ln 1 plus x to the 6th dx, is approximately 0.2 to the 7th power, because that -1 squared is just 1. So 0.2 to the 7th power over 7, which is approximately 0. We have 5 zeros. 1, 2, 3, 4, 5, and then 18. So since it said to 6 decimal places, we should round to the 6th decimal place. So that would be 1, 2, 3, 4, 5. That would be to this place. So if we're rounding to the 6th decimal place, we can round that 1 up. So our actual answer would be more zeros. 1, 2, 3, 4, 5, and then a 2. So that would be more like it, because we're rounding to 6 decimal places. All right, so this is a super powerful thing. I know that math isn't always that fun for you, but come on now. This is really cool that this sum that is infinitely many terms long, we can approximate it to be very close with only the first term. And if you look back up, we wouldn't be able to evaluate this integral at all. So this powerful idea that we can write a function as a series allows us to evaluate this integral that we otherwise wouldn't be able to. So very cool. All right, thanks for hanging out and doing some cool math. I hope you found it more entertaining than my dogs. They are over here, totally knocked out.